So in this video, we're going to look at what's called the first derivative test, which will allow us to identify local extrema based on the sign of the first derivative, meaning positive or negative. So first, let's write out what the test is. So suppose that f is a continuous function over an interval I containing a critical point C. If f is differentiable over I, except possibly at C, so it does not need to be actually differentiable at the critical point. Think something like the absolute value, where we know it has a minimum at x equals 0, where it's not differentiable at 0. So if f is differentiable over I except possibly at C, then f of C satisfies one of the following. Okay, so we're going to have three possible cases for f of C. So C is our critical point. So f of C, meaning the f value at C, could have one of these cases, which is basically going to be that it is a local minimum, a local maximum, or neither. Okay, so if f prime changes sign from positive when x is less than C, so it's positive to the left of C, to negative when x is when x is greater than C. So it's positive to the left of C, the derivative is positive to the left of C and negative to the right of C. Then f of C is a local maximum. Okay, and this should make sense if you just draw a quick little picture of what this would mean, right? If you have some point f of C, and to the left of it, the derivative is positive, meaning that it's increasing, and to the right of it, the derivative is negative, meaning that it's decreasing. That definitely looks like a maximum, right? Okay. So 2, if f prime, I'll just shorten this a little, 2 is negative when when x is less than C, and positive when x is greater than C, then f of C is a local minimum of f. Okay, so again, if you just draw a quick picture here, if you have C, so the derivative is negative on the left, positive on the right, it'll look something like this, again giving us that picture of a local minimum. Okay, so the third option would be if f prime has the same sign for x is less than C and x is greater than C, then f of C is neither a local minimum or local maximum. Okay. So, if we just think about where would this one happen, well, maybe something like, x cubed, for example. Okay. So if f of x equals x cubed, this graph looks like, let me draw it a little better, like this, right? That's x cubed. The derivative of f prime of x is 3x squared. 3x squared is a quadratic centered with vertex at the origin. So if we made a sign chart for this, it would have 0 as its only 0, and it's positive on both sides of it. So here, this is neither a minimum or a maximum. So we can see that, that this third condition is satisfied for x cubed. So c equals 0 is a critical point of x cubed, but we need not have a local min or max. Now, it does kind of appear on the graph still. It'll kind of look like it's flattening out a little bit. So you can kind of see that if you look at the x cubed graph, it looks like it's kind of flattening out. So it is kind of reflected in the shape still, but not very definitively, right? There's not like a criteria for it'll be this flat for this long or anything like that. But it does kind of show up. But yeah, it will follow this third condition here for this one. So now we can go ahead, maybe we'll just look at some previous examples first real quick, like this one that we did in the last video. Okay, so this one, x cubed minus 4x squared plus x minus 4, we found the critical numbers as 4 minus root 13 over 3 and 4 plus root 13 over 3. So this one, because it's going from positive to negative, we can see that this is going to be a local max. Okay, and this one, because it's going from negative to positive, is going to be a local min. Okay, and this is reflected on the graph, of course, as well. Okay, so if we just look at it right here, this is the first critical point, and that does indeed look like a local max. And this is the second one, and that does indeed look like a local min as well, right? So if we just go ahead and like look at the actual graph of f prime of x overlaid on top of it, let me change the color of that. You can see exactly how that's reflected in the graph of the derivative, right? So this is what our sign chart is based on. The derivative is negative, the derivative hit 0, then the derivative was positive, then it hit 0, the derivative is negative. So this kind of shape would tell us that this is a local max at that same point. And then the derivative, actually, it also has a point where it hits 0, and that's what's called an inflection point that we'll talk about in a future video. But then it goes, we're only really concerned about the sign now, so it's negative all the way until right here, again lining up with that local min, and then it's positive, meaning it's increasing after that. Okay. So let's go ahead. We can do some more examples here. And note that this criteria here for the first derivative test does indeed require f to be a continuous function. So when we look at things like 1 over x, that's not really satisfied here, right? 1 over x is not continuous, namely over x equals 0. So we can't apply the first derivative test to it, even though the rest of the conditions would be satisfied, right? It's differentiable everywhere except at 0, has a critical point at 0, and it does Well, it doesn't actually change sign on either one of them, right? But some rational functions will. But regardless, we can't say that there's any kind of local min or max there because it's not continuous in the first place. So we can't apply that first derivative test to it. If there's a different interval where it's continuous, you could apply it over that interval. But namely, at 0, we wouldn't be able to. So again, the function doesn't need to be differentiable at 0. So if you have something like the square root, the absolute value of x, right? The derivative of this is x over the absolute value of x, which it's easier to see this if you write it with the piecewise form, which is just 1 if x is greater than 0 and -1 if x is less than 0. And if you actually look at the point 0, you'll see it's not differentiable at 0. So if we do a sign chart for f prime, 0 is a critical point because it's not differentiable there, right? It's undefined there. And that is a criteria for being a critical point. And it's positive to the right of 0 and negative to the left of 0. So we do have a local min at 0. Okay, so we do not need differentiability at the point in order to have a local extrema. But we do need continuity at that point. Okay, so let's see. So I'm just looking at some examples in this text here that I'm referencing. Let's do this one. F of x equals the cube root of x minus 1. They all will kind of work the same way, so it doesn't really matter which problem we do. So we just go ahead and take the derivative. And this one's going to be, this is x minus 1. It might be easier to think of it as x minus 1 to the 1/3, right? So this is going to be 1/3 times x minus 1 to the -2/3 times 1. By the chain rule, the derivative of x minus 1 is 1. So in other words, this is 1/3 times the cube root of x minus 1 squared. Right. So this one, if we go to do a sign chart here for f prime, our only critical point should be at the point x equals 1, right? Because that's going to make this 0, which is going to make the whole denominator 0. So we'll put 1 here. Sometimes, some people like to label whether or not this is a 0 or a undefined number. So you could label it with a frowny face for a bad number, and you could just put a 0 there for a 0. Not really necessary in this context right here, but when we kind of put this all together and look at how to really make a good picture of the graph, it'll be more useful there because it'll be actually important whether it's undefined or 0 there. So if we look at the sign of this, you might be able to see, okay, whatever we put in for x here, it doesn't really matter because when we square it, it's going to be positive, right? So this is always going to be positive no matter what. Again, because of that squared there. Squaring things make things positive. So this is always going to be positive. So it's going to have the same sign on both of them. Okay, so this is going to be always increasing. So this is going to be neither, right? So this one's not going to have any local extrema. So if we just go ahead and throw this on the graph, not sure if you can do a cube root function here. So I'll just go ahead and do it to the 1/3 power. Whoops. X minus 1 to the 1/3 power. Okay, so it looks like this. So again, you can see that there's nothing that looks like it would be a local max or min here. It is always increasing. And at 1, this is where it gets so vertical that the derivative does not exist. Just like we saw in the x cubed function itself. This is just the x cubed function moved to the right one. So, okay, let's do one more example here. So let's look at another kind of a weird one. And a lot of times it'll just be asking for like a polynomial or something, and those are a little bit easier to do as long as they're factorable. So let's look at this one, and it's important to note that this specifies x has to be greater than 0, which would make sense because the square root function has to be greater than or equal to 0, and 0 doesn't work in the 1 over x part. All right. So if we go ahead and take the derivative of this, okay, so you just take the derivative of each part separately here. This is x to the 1/2, so you're going to bring the 1/2 down. So this is going to be 1/8 combining with the 1/4, and then over root x, because then it'll be 1/2 minus 1, which is negative 1/2, so x to the negative 1/2 power. Minus 1 over x squared, right? So we just take the derivative of each part separately here. So our critical numbers, or I guess I should say number, would be 0, right? That's the only point, right? Well, not necessarily. I guess this could be 0. I was thinking because neither denominator or numerator has an x in it, it wouldn't be 0, but their difference could still be 0, right? So just thinking of the sign chart for f prime, 0 will definitely be on there as a bad number. But we do need to consider the fact that the derivative itself just could be 0. So we need to find a common denominator here. So we get x squared minus 8 root x. Hope it's okay if I skip these steps for the algebra parts, but I'm just multiplying this one by x squared over x squared, this one by 8 root x over 8 root x. Okay. And then that'll give us a common denominator of 8 root x times x squared. So when we're looking at this equaling 0, we're really only worried about the numerator equaling 0 now that it's all over one fraction, right? A fraction is 0 if the numerator equals 0. In other words, you can multiply both sides by 8 root x times x squared, and on the right side it would be 0 times that, which is 0, and on the left side it cancels out. So we only need to consider the numerator here. X squared minus 8 root x equals 0. Okay, so a few ways we could go about this. We can bring that 8 root x over. Now maybe we square both sides. So I'm thinking we get rid of the root first. So there's going to be different ways you can do it, of course. So x to the 4th minus 64x equals 0. Now we can factor an x out. Okay. So this says that either x equals 0, which we already have, so we don't need to worry about that part. That's not even in our domain, so this one we can just completely forget about it. Or x cubed minus 64 equals 0, meaning that x cubed equals 64. And you take the cube root of both sides here, you'll get x equals 4. Okay. So 4 is a 0 of f prime, so that needs to go in there as well. Okay. So now this one's definitely a little bit strange if you think about the multiplicities, if if anybody looked into that, because there is a multiplicity at 0 with the x squared, but there's also this square root thing going on, so it's hard to definitively say that. So we're going to test points in every interval this time instead of relying on it alternating. Now we don't need to look to the left of 0, of course, because that's not even in our domain. Okay, so we can just forget about that. So let me just like X that out. But we do need to look between 0 and 4 and then 4 onwards. Okay. So we'll plug in, say, like 1. So we'll plug in like f prime of 1 to see what the sign is. So we get 1/8 minus 1. So that's definitely going to be less than 0. And again, it doesn't matter what the value is. It just matters if it's negative or positive. So you don't even need, like, no need to go ahead and find a common denominator and all that. So now we'll do f prime of, say, like 5. Or maybe it would actually be easier to use a perfect square because we have that square root. So let's use 9. So 1/8 times the square root of 9, so 3, minus 1/81, which is 9 squared. So this is going to be 1/24 minus 1/81. So again, you don't need the actual value. That one's of course going to be positive because 1/81 is less than 1/24 since they're both in the denominator. So it's going to be positive to the right of 4 here. All right, so this function, things we might need to write down eventually, is increasing from it's increasing from 4 to infinity and decreasing from 0 to 4. Okay, and then there is a local minimum at 4. Okay. So we can go ahead and look at what this graph looks like. Eventually we want to work up to like drawing a full picture of the graph using this information. But let's just go ahead and look at this. So this is what it looks like here. Okay. So we can see it is, it's a little bit of a strange graph actually, because it looks like it's flattening, but it actually does start increasing. It's just very subtle. So 4 is where we have the local min, and this is why it's helpful to look at the math and not always just the graph, because it would be very hard using the graph here to pinpoint that the local min is at 4, right? Because it gets very flat around 4, but that's indeed what it is. And it's decreasing up to that point and then increasing afterwards. Okay.